A differential equation is an equation involving derivatives, so it connects a quantity with the way that quantity changes. Think of a curve as the path of a moving point. An ordinary differential equation uses derivatives with respect to one independent variable, such as x. For example, dy by dx equals 1 minus x squared divided by 1 plus y squared uses only x as the independent variable. A partial differential equation uses partial derivatives when there is more than one independent variable. We also classify an equation by order and degree. The order is the highest derivative present. The degree is the power of that highest derivative after the equation has been made polynomial in the derivatives. In the circuit equation, L d squared q by dt squared plus r dq by dt plus q divided by c equals e sine omega t. The order is 2 and the degree is 1. In the equation 1 plus dy by dx squared, all cubed, equals d squared y by dx squared, all squared, the order is 2 and the degree is 2. These labels tell us which solving tools may be appropriate. A family of curves is a collection described by a relation containing arbitrary constants. The set x squared plus y squared equals c is a one-parameter family of concentric circles when c takes positive real values. The parameter c chooses the circle, but the equation itself describes the whole collection. A useful principle from the notes is that an n-parameter family can usually produce an nth-order differential equation after eliminating those parameters by differentiation. Let us see that idea with circles passing through the origin and having their centers on the y-axis. A circle with center 0, a has equation x squared plus y minus a squared equals a squared. Differentiating gives 2 times plus 2 times y minus a, dy by dx equals 0. Eliminating a leads to x squared minus y squared multiplied by dy by dx equals 2xy. So the correct equation is option B, not the alternatives. Notice the pattern. Describe the family, differentiate, then eliminate the arbitrary parameter. The differential equation remembers the family without naming the particular circle. The first solving method in the notes is separation of variables. Its goal is to put every expression involving y with dy on one side and every expression involving x with dx on the other. In symbols, we aim for f of y dy equals phi of x dx. Then we integrate both sides. The integral of f of y dy equals the integral of phi of x dx plus c. The constant is essential because indefinite integration produces a family of solutions. Consider the notes example 3. The equation is e to the power dy by dx equals x plus 1, with y equal to 3 when x equals 0. Taking the natural logarithm gives dy by dx equals ln of x plus 1 dx. Integrate by parts. The integral of ln of x plus 1 dx is x ln of x plus 1 minus the integral of x divided by x plus 1 dx. Rewrite x as x plus 1 minus 1. The result is x ln of x plus 1 minus x plus ln of x plus 1 plus c, or y equals x plus 1 times ln of x plus 1 minus x plus c. At x equals 0, y equals c, so c equals 3. The particular solution is y equals x plus 1 times ln of x plus 1 minus x plus 3. A first-order equation is called homogeneous in this section, when the numerator and denominator are functions of x and y having the same degree. The standard substitution is y equals vx, where v represents the ratio y divided by x. Because y equals vx, differentiating gives dy by dx equals v plus x dv by dx. This is the key move. It changes an equation in two variables into an equation involving x and v, which can often be separated. In example 7, x dy minus y dx equals the square root of x squared plus y squared times dx. Divide by dx and write dy by dx as y divided by x plus the square root of 1 plus y divided by x, all squared. Now substitute y divided by x equals v. The left side becomes v plus x dv by dx, while the right side becomes v plus the square root of 1 plus v squared. The v terms cancel, leaving dv divided by the square root of 1 plus v squared equal to dx divided by x. Integrating gives log of x, plus a constant equal to the inverse hyperbolic sine form log of v plus square root of v squared plus 1. Replacing v by y divided by x produces the implicit solution x squared times c equals y plus the square root of y squared plus x squared. Now we reach the main method of this lesson, a linear differential equation of the first order. Its standard form is dy by dx plus p of x times y equals q of x. The dependent variable y and its derivative appear only to the first degree, and they are not multiplied together. The functions p and q depend only on x, or they may be constants. The integrating factor is the tool that turns the left side into one product derivative. It is written if equals e to the integral of p of x dx. Once the integrating factor is found, multiply the entire equation by it. The left side becomes the derivative of if times y. Integrating gives if times y equals the integral of q times if dx plus c. This is not a formula to memorize blindly. The integrating factor is chosen precisely because the product rule says the derivative of if times y is if times dy by dx plus if prime times y. Since if prime divided by if equals p, the two terms match the standard equation. In the next scene, we will use this mechanism on example 10, keeping every algebraic step visible. Let us solve the exact example emphasized in the notes. X plus 1 times dy by dx minus y equals e to the x times x plus 1, all squared. First, divide every term by x plus 1. We must work on an interval that does not contain x equals -1, because division by x plus 1 would otherwise be invalid. The equation becomes dy by dx minus y divided by x plus 1 equals e to the x times x plus 1. Now, compare term by term with dy by dx plus p of x times y equals q of x. The coefficient of y is -1 divided by x plus 1, so p of x equals -1 divided by x plus 1. The right-hand side is q of x equals e to the x times x plus 1. This comparison is the most important organizational step. Do not calculate the integrating factor before the equation is in standard form, because the coefficient multiplying y is what determines p. Also notice that q is not e to the x times x plus 1 squared anymore. One factor of x plus 1 disappeared when we divided the original equation. We now have the two ingredients needed for the integrating factor. P equals -1 over x plus 1, and q equals e to the x times x plus 1. We now calculate the integrating factor carefully. Since p of x equals -1 divided by x plus 1, the integrating factor is e to the integral of negative dx divided by x plus 1. The integral is negative ln of the absolute value of x plus 1. On an interval where x plus 1 is positive, the integrating factor is e to the negative ln of x plus 1, which equals 1 divided by x plus 1. The same local method works on any interval avoiding -1, with the usual absolute value interpretation. Multiply the standard equation by 1 divided by x plus 1. The left side becomes y divided by x plus 1. On the right, q times the integrating factor is e to the x times x plus 1, multiplied by 1 divided by x plus 1. The factors cancel, leaving e to the x. Therefore, y divided by x plus 1 equals the integral of e to the x dx plus c, which is e to the x plus c. Finally, multiply by x plus 1, y equals e to the x times x plus 1 plus c times x plus 1. This is the complete family of solutions. The constant c is not an error term. It records the different solution curves produced by different initial values. A reliable solution should be checked, not merely boxed. Start with y equals e to the x times x plus 1 plus c. Differentiate using the product rule. The derivative of e to the x times x plus 1 is e to the x times x plus 1 plus e to the x, so dy by dx equals e to the x times x plus 2. The derivative of c is 0. Substitute into the original equation. The first term is x plus 1 multiplied by e to the x times x plus 2. Then subtract y, which is e to the x times x plus 1 plus c. the expression becomes e to the x times x plus 1 times x plus 2 minus e to the x times x plus 1 minus c. This simplifies to e to the x times x plus 1 squared minus c. The original equation has no free constant on the right, so here we must notice an important point. The direct family from the integrating factor formula is y equals e to the x times x plus 1 plus c times x plus 1, not plus a bare c. The integrating factor equation was y divided by x plus 1 equals e to the x plus c. Multiplying gives y equals e to the x times x plus 1 plus c times x plus 1. With this corrected form, differentiation gives e to the x times x plus 2 plus c, and substitution cancels the c terms exactly. Thus, the verified general solution is y equals e to the x times x plus 1 plus c times x plus 1. For the representative member c equals 0, y of 0 equals 1, so the point 0, 1 lies on the curve. At x equals 1, y equals 2e. Another first-order method is the exact differential method. Write an equation as m of x, y dx plus n of x, y dy equals 0. It is exact when the partial derivative of m with respect to y equals the partial derivative of n with respect to x. That condition means the two-variable expression is the differential of a single potential function. In example 15, m is x squared plus 2xy, and n is x squared plus y squared. Differentiate m with respect to y. The result is 2x. Differentiate n with respect to x. The result is also 2x. Therefore, the equation is exact. To find the potential, integrate m with respect to x, treating y as constant. The integral of x squared plus 2xy is x cubed divided by 3 plus x squared y. Then inspect n. The term still needed after differentiating this expression with respect to y is y squared. Integrating that with respect to y gives y cubed divided by 3. Hence, the solution is x cubed divided by 3 plus x squared y plus y cubed divided by 3 equals c. The equality of cross partials is the test. The potential function is the answer. The notes also list useful exact differentials, such as d of xy equals x dy plus y dx, and d of y divided by x equals x dy minus y dx, all divided by x squared. Recognizing these patterns can save several lines of integration. The same idea of changing a differential equation appears in orthogonal trajectories. Two curve families are orthogonal trajectories when each curve of one family meets each curve of the other at right angles. For the family xy equals c, differentiate with respect to x. Y plus x dy by dx equals 0, so dy by dx equals negative y divided by x. A perpendicular slope is the negative reciprocal, so replace dy by dx with negative dx by dy. This gives negative dx by dy equals negative y divided by x, or y dy equals x dx. Integrating produces y squared divided by 2 equals x squared divided by 2 plus c. Therefore, the orthogonal family is y squared minus x squared equals 2c. The original curves xy equals c are rectangular hyperbolas. The new curves are another hyperbola family crossing them at right angles. The notes next move to linear second-order equations with constant coefficients. D squared y by dx squared plus p dy by dx plus qy equals 0. The standard trial solution is y equals c e to the mx. Differentiating brings down factors of m, so substitution gives c e to the mx times m squared plus pm plus q equals 0. Since the exponential and c are not the part we want to set to 0, the auxiliary equation is m squared plus pm plus q equals 0. The roots determine the form of the solution. If the roots are real and unequal, use c1e to the m1x plus c2e to the m2x. If the root is repeated, use c1 plus c2x, all multiplied by e to the mx. If the roots are alpha plus or minus I beta, use e to the alpha x times a cos beta x plus b sine beta x. For example 20, the equation is d squared y by dx squared minus 7 dy by dx plus 12y equals 0. The auxiliary equation is m squared minus 7m plus 12 equals 0, which factors as m minus 3 times m minus 4. The roots are 3 and 4, so the solution is y equals c1 e to the 3x plus c2 e to the 4x. A non-homogeneous second-order equation has a forcing term, d squared y by dx squared plus p dy by dx plus qy equals r of x. In operator notation, write f of d times y equals r of x, where d means differentiation with respect to x. The complete solution has two parts. The complementary function, or CF, solves the associated homogeneous equation. The particular integral, or PI, supplies one response to the forcing term. For an exponential forcing e to the x, the notes give the efficient rule. 1 over f of d applied to e to the x equals e to the x divided by f of a, provided f of a is not 0. In example 23, the equation is y double prime minus 3y prime plus 2y equals e to the 5x. The auxiliary polynomial is m squared minus 3m plus 2, with roots 1 and 2, so the complementary function is c1 e to the x plus c2 e to the 2x. For the particular integral, evaluate the polynomial at 5, 25 minus 15 plus 2 equals 12. Thus, the particular integral is e to the 5x divided by 12. The complete answer is c1 e to the x plus c2 e to the 2x plus e to the 5x divided by 12. For sine or cosine forcing, the same operator idea is used with d squared replaced by minus a squared, while polynomial forcing is handled by expanding the inverse operator as a finite series. Cauchy-Euler equations have powers of x multiplying derivatives. For example, a 2x squared y double prime plus a 1xy prime plus a 0y equals q of x. The substitution in the notes is x equals e to the z, or z equals natural log of x. Since 1 over x equals dz by dx, we obtain x dy by dx equals dy by dz. A second differentiation gives x squared d squared y by dx squared equals d squared y by dz. The equation therefore becomes a constant quotient second-order equation in z. A 2d squared y by dz squared plus a 1 minus a2 dy by dz plus a 0y equals q of z. Example 30 is x squared y double prime minus 2xy prime minus 4y equals x to the fourth. After substitution, the left side becomes y double prime with respect to z minus 3y prime with respect to z minus 4y, and the right side becomes e to the 4z. The auxiliary equation is m squared minus 3m minus 4, which factors as m minus 4 times m plus 1. The complementary function is c1 e to the 4z plus c2 e to the negative z. The forcing term resonates with the root 4, so the particular integral includes z e to the 4z divided by 5. Returning to x gives y equals c1x to the fourth plus c2 divided by x plus 1/5 x to the fourth, natural log of x. When the forcing term is difficult to handle with operator shortcuts, the notes introduce variation of parameters. Start with two linearly independent solutions, y1 and y2 of the associated homogeneous equation. The complementary function is ay1 plus by2. For a particular solution, replace the constants by functions, uy1 plus vy2. The formulas use the Wronskian, which is y1 times y2 prime minus y1 prime times y2. Specifically, u is the integral of negative y2r divided by the Wronskian, and v is the integral of y1r divided by the Wronskian. Example 32 solves y double prime plus y equals tangent of x. The auxiliary equation is m squared plus 1 equals 0, giving y1 equals cosine x and y2 equals sine x. Their Wronskian is 1. Thus, u equals negative the integral of sine x times tangent of x dx. Rewrite this as negative the integral of sine squared x divided by cosine x dx, which equals negative ln of secant x plus tangent x plus sine x. Also, v equals the integral of cosine x times tangent of x dx, which is negative cosine x. Combining u cosine x and v sine x, the sine x terms cancel, leaving the particular solution negative cosine x times ln of secant x plus tangent x. Therefore, y equals a cosine x plus b sine x minus cosine x ln of secant x. The final section classifies points for a normalized second-order equation y double prime plus p of x y prime plus q of x y equals 0. If p and q remain finite at x equals x0, that point is ordinary. If either coefficient becomes infinite, it is singular. A singular point is regular if the products x minus x0 times p and x minus x0 squared times q remain finite. Otherwise, it is irregular. Apply this to example 33. X times x minus 2 squared y double prime plus 2 times x minus 2y prime plus x plus 3 times y equals 0. After dividing by the leading coefficient, p equals 2 divided by x times x minus 2, and q equals x plus 3 divided by x times x minus 2 squared. Both coefficients are infinite at x equals 0 and x equals 2, so both are singular candidates. At x equals 2, multiply p by x minus 2. The remaining expression is 2 divided by x, finite at 2. Multiply q by x minus 2 squared. The result is x plus 3 divided by x, also finite at 2. Therefore, x equals 2 is a regular singular point. At x equals 0, xp equals 2 divided by x minus 2, finite, and x squared q equals x times x plus 3 divided by x minus 2 squared, also finite. Therefore, x equals 0 is regular singular as well. The important workflow is normalize, locate divergences, then test the two weighted products. Let us organize the whole chapter as a practical workflow. First, identify the order, degree, and whether the equation is ordinary or partial. For a first-order equation, look for structure. If the variables can be placed on opposite sides, use separation. If the right-hand side is a ratio of same-degree functions, try y equals vx. If the equation is m dx plus n dy equals 0, test whether the partial derivative of m with respect to y equals the partial derivative of n with respect to x. If the equation can be written as dy by dx plus p of xy equals q of x, use the integrating factor. That is the central tool from our main example. Rewrite, identify p and q, compute e to the integral of p dx, multiply, integrate, and verify. For second-order constant coefficient equations, form the auxiliary polynomial and classify its roots. For non-homogeneous equations, add a particular integral to the complementary function. For Cauchy-Euler equations, use z equals natural log of x. For difficult forcing terms, vary the parameters. Finally, when studying a normalized second-order equation near a point, test whether the coefficients and their weighted versions stay finite. A method is not chosen by appearance alone. It is chosen by the structure that makes the next step simpler. The key lesson is a repeatable sequence. For a first-order linear differential equation, begin with dy by dx plus p of xy equals q of x. If necessary, divide through so the coefficient of dy by dx is 1. Read off p and q. Compute the integrating factor e to the integral of p of x dx. Multiply every term by that factor, so the left side becomes the derivative of integrating factor times y. Integrate, add the arbitrary constant, and solve for y. In example 10, the equation became dy by dx minus y divided by x plus 1 equals e to the x times x plus 1. Therefore, p was negative 1 over x plus 1. Q was e to the x times x plus 1, and the integrating factor was 1 over x plus 1. The result was y divided by x plus 1 equals e to the x plus c. So the verified solution was y equals e to the x times x plus 1 plus c times x plus 1. Remember the final verification, differentiating and substituting returns exactly e to the x times x plus 1 squared. Whenever you are unsure, return to the structure. Normalize, identify, multiply, integrate, and check. You can now recognize the main differential equation families in the notes and match each one with a method. Most importantly, a first-order linear equation is systematic rather than mysterious. Put it into standard form, calculate the integrating factor, turn the left side into a product derivative, integrate, and verify. For example 10, the answer is y equals e to the x times x plus 1 plus c times x plus 1. Keep the structure visible, and the algebra becomes a sequence of manageable decisions.